Hi, welcome back. This is the final part 5 of 3 heads problem. In the last part, we have seen a beautiful, simple, strategical way that exactly mimics the recursive thinking behavior. The basis of that strategy is the fact that the person whose number is the sum of the other two will always be the first person to claim his number. So each student can initially assume his number is not the sum of the other two and calculate the conversation length for it. He waits till that conversation, and if no one has claimed their number, in the next turn he claims his number as the sum of the other two. So this strategy will mimic the behavior of the recursive thinking exactly. In this final part, I want to introduce another variation of this puzzle. This is going to be very interesting. Okay, let us see the puzzle. A dictator calls 3 prisoners and puts a hat on each of their head. He writes a positive integer on each of their hat. So each prisoner can see the other two numbers but can't see his own. The same as the previous puzzle. They are not allowed to communicate in any way. Now, the dictator says one of your number is the sum of the other two. He tells, I will count from 1 to 10. Within that, someone must come forward to tell your number. If that is correct, all the 3 of you will be released. If it is wrong or no one is coming forward, then you will all be shot dead. So the dictator starts counting 1, 2, 3 and so on. No one seems to come forward, but at the count 10, one prisoner comes forward and tells my number is 96. The dictator, much to his disappointment, has to release all the 3 prisoners. So what are the other numbers? In the original puzzle, the professor asks each student in order: Albert, Brinda and King. But in this puzzle, in this variation, any prisoner can come forward to tell his number as soon as he deduces his number. So, and unlike the original problem, this one has unique solution. Remember, one of the prisoner claims his number as 96 at 10th count. So this is the puzzle. I am not going to reveal the answer to this puzzle, but let us see how this can occur. In the last part, we got a simple recurrence equation to calculate the conversation length. So here this part can either be 1 or 2 depending on the max function. That is, which of the numbers is the largest. That means the next turn can come at the next conversation or after that. Now, in this countdown version of the puzzle, the prisoners don't have to wait for their turn. Each one tells a number as soon as he deduces. So this becomes 1. Also, the initial case, so this becomes 1. Also, the initial case becomes this. That is, if any of the prisoner sees the other two numbers as equal, then he can right away claim his number as the sum in the count 1 itself. So we got this simple recurrence equation. I tried to solve this to see whether we can get any closed form function or something, but could not get one. However, I got some nice way to calculate this. Let me illustrate with an example. Let me illustrate with an example. Before going to that, let us define a function f. F of m comma n is equal to f of n comma m for all m and n, where m and n are non-negative integers. F of 0 comma n is equal to 0 for all n. Finally, this is the definition. F of m comma n is equal to floor of n by m plus f of n mod m comma m, provided m is not equal to 0 and m is less than or equal to n. Note that this floor function is the quotient when we divide n by m. This n mod m is the remainder when we divide n by m. So this is the function we need. Suppose if the prisoner sees the numbers a and b with a less than or equal to b, then his waiting time is simply f of a comma b minus a. To illustrate, if the person sees 62 and 89, his waiting time is f of 62 comma 89 minus 62, which is f of 62 comma 27. Since f of m comma n is equal to f of n comma m, f of 62 comma 27 is f of 27 comma 62. F of 27 comma 62 is floor of 62 by 27 plus f of 62 mod 27 comma 27, applying the function definition. 62 mod 27 is 8. So again applying the recursive function, we get this. 27 mod 8 is 3. Again applying the recursive function, we get this. 8 mod 3 is 2. Again applying the recursive function, we get this. 3 mod 2 is 1. So again applying the recursive function, we get this. 2 mod 1 is 0, and finally f of 0 comma 1 is 0, and solving this we get 10. So the strategy for the prisoner is to wait till the 10th count, and if no one claims, then at 11th count claim the number as the sum of the two numbers, that is 62 plus 89, which is 151. Each prisoner follows the same. If they do so, they will always be right, and this will mimic the behavior of the recursive thinking. That calculation part can be easily derived, and that is to show how easy the strategy is. The beauty of this problem is the waiting time can be the actual time rather than counting. For example, if the prisoners take the waiting time in seconds, each person has to wait till their waiting time, and if no one has claimed, then in the next second he claims his number as the sum of the other two. This feels magical to me. The three prisoners just simply stand there for some time with no communication, then suddenly someone comes forward and tells his number, and he is right. So with this excitement, let me end this series. I hope I have shared my excitement with you. This problem is a type of induction puzzle which requires recursive thinking ability with the understanding of theory of mind. This also shows the power of strategies, and that is so amazing. So keep pondering. Thank you.